So, in this session, we are going to talk about another toy problem. So, in the previous session, we discussed about the monkey and the banana problem. So, that was a classical AI problem where an AI agent had to plan a sequence of actions to achieve the goal. If you have not watched that session, always you can watch it. So today in this session, we are going to discuss about the vacuum cleaner world problem. So a vacuum cleaner, it's an object, but in AI, the vacuum cleaner world becomes an perfect teaching tool to introduce the concept of intelligent agents. So those agents operate in a specific AI environment, perceiving its surroundings and taking actions. So by the end of this session, you will understand what a rational agent is, how problem formulation works in AI, how to represent states, actions, how to write a simple reflex agent program. So all these things you will be able to have an idea. So to recap, we discussed about what was a toy problem and a real world problem. So a toy problem has one defining characteristic. So it can be given a concise, exact description because everything about the problem is known. The starting state, the goal state, the possible actions, rules, nothing is ambiguous. Everything is clear. When you compare that with a real world problem, a problem whose solutions are what people think about. Supposingly, you take an example of medical diagnosis or a routing problem in a city or translating between the human languages. So these problems tend to have a single agreed, not to have a single agreed upon description because different people define them differently. The rules keep changing and the environment here is unpredictable. So the reason we study toy problem first is strategy. See, when you are learning to ride a bicycle, you do start, you do not start actually on a very busy route. You start in a very small space like a parking lot. So toy problems are our parking lot for AI to go to face the real world. Today's discussion, we are going to talk about the vacuum cleaner world. So, though it is very simple enough to understand, so teaching the core mechanics is again a very challenge. Before we jump into the vacuum cleaner world, I would like to go through those uh, characteristics once again because all these characteristics plays important role in any of the toy problems. So first of all, toy problems are not real world problems and then they are generated for educational or fun purpose. They are played either on board or paper. So means the environment is completely bounded, finite and visible. And the environment is controlled because there is no ambiguity or surprises. Problem formulation is possible because the boundary conditions and the constraints are known in advance. So they can be converted to computer programs so that you can write actual code to solve them. More examples like tic-tac-toe problem, 8 puzzles are all the classical examples. So today in today's session, we are going to talk about the vacuum cleaner world. So they are used These characteristics are used as problem solving ventures in developing algorithms and testing the intelligent agent's behavior. Okay, right. Now we'll get into the problem of vacuum cleaner world. So consider there are two rooms. Okay, here the robot can be in either of the room. Okay. So the rooms can be dirty or it can be clean. The aim is or the goal of the agent is to clean the room. That's all. If there is dirt, it should clean. So this is a very simple possible version, very simple problem statement. This is the entire world. Okay. So the tiny world captures everything that matters about the intelligent agent design, perception, decision making, action, and goal achievement. So the vacuum cleaner world is a basic problem in artificial intelligence and it is used to explain how intelligent agent works. So who's an intelligent agent? An intelligent agent in this particular concept or context is any system that perceives its environment through sensors and act upon that environment through actuators. So you're going to do the actions through the actuators. Sensors gives your input. So our vacuum cleaner agent operates in an environment containing rooms. So each room can either be clean or dirty. So there are no in-between states, be clean or dirty. No partial cleanliness. So the problem's output is going to be binary. Either it's going to be clean or it's going to be dirty. The goal of the agent is to clean all the dirty rooms using minimum number of actions. That's minimum time. So since it is minimum number or minimum time, minimum actions, the agent should not be wasteful. It should not be simply re-cleaning the room that are already clean. So it should not get into like a loop. The objective of the intelligent agent is to show the efficiency in solving the problem. This introduces us to one of the core evaluation criteria for AI agents, that is rationality. A rational agent is one that does the right thing given what it knows. In this case, right thing is to clean dirty rooms efficiently and avoid pointless actions. So this is a kind of reasoning we want to build into a very intelligent system. From it can be from robots to chatbots to recommendation engines, anything. Okay. Now, what the environment will really have? The environment usually contains two rooms, A and B, A on the left and A on the left and B on the right. Okay. This is minimal, small but interesting. The vacuum cleaner agent has four possible actions. So these are the actions. Okay. Move left. The agent moves from B to A. Okay. If it is already in room A, this action has no effect. Next we'll talk about move right. The agent moves from A to B. If it is already in B, then there is no effect. Now, the first two actions are about moving, either left or right. Now, suppose if in any of the rooms, either it has been room A or room B, whether it is a left or right. Now, when you have to suck the dirt, so in whichever room it is, A or B, the agent has to suck the dirt if there is a dirt. But if the room is already clean, this action has no effect. Okay. Stay idle. The agent does nothing. The agent might be taken when there is nothing to left to clean. Like it has clean, the rooms are clean. So these four actions define the complete action space of our agent. Everything the agent can ever do in its is the capture of this captured list. That is left, right, suck the dirt, be idle. Can the agent perceive the state of both rooms at once? Or not? Is it possible? Or whether it can only perceive its current room wherever it is. So whenever we are designing, this is an important question. So the answer determines what kind of agent we can build and how complex it needs to be built. In the simplest version, if the agent knows only its current location and whether the room it is in is dirty or clean. So it does not have a global view of the entire world. The environment in this case is partially observed. Okay. So the main objective of the vacuum agent has three parts. So we'll understand how actually the agent works, what's its real decision making logic and what is its objective. That's what we're going to discuss here. So the objective is detect dirt in the room. The agent must be able to sense whether the current room is clean or dirty. First is detecting the dirt. Next is cleaning the dirt. When the dirt is detected, it has to do the suck action. Then it should minimize the cost, time and unnecessary movement. Why? Because to improve the efficiency. Now, let us look at the working logic. The agent checks the current room. Is it dirty or clean? Supposing if the room is dirty, it performs the suck action. Okay. Then the room is clean now. And if the room is clean, either after sucking or before sucking, it moves to the other. So this process continues until all rooms become clean. So it's a very simple logic. There is no complex reasoning, no planning ahead, no memory of past states. The agent simply reacts to what it currently perceives. That's very important. So this type of agent is called as simple reflex agent. So simple reflex agent works on the current perception. So it is the most basic kind of intelligent agent in AI. Despite its simplicity, the agent works perfectly in two rooms. That is a deterministic environment. Okay. So if you match the right agent design to the right problem environment, then obviously there is efficiency is going to get improved. Think of, let's suppose the agent starts in room A and room A is dirty. What will happen? It performs a subtraction. Then it moves to the next room. Simple, right? Next, we will talk about the formulation, that is problem formulation. So we are going to talk about the states and actions. So formulating a problem in AI is very, very important. So it needs 5 components. Know the state, initial state, actions, transition model, and goal state. So let us go through these states one by one. The state, first we'll talk about state. The state of the world is defined by 2 things: the agent's current location and the cleanliness status of the room. Okay. The agent can be in room A or room B. That is 2 options, 2 locations. Each of the 2 rooms can be clean or dirty. 2 possible actions per room. So what will be the total states? That is 8 possible world states will be available. So for environment with n locations, the total state will be n into 2 power n states. So for 3 rooms, it will be 3 into 8. Okay. 24 states. For 4 rooms, then you can calculate as it goes. So what is the observation made here is that state space quickly grows. So already we have understood there are 8 possible states. So initial state might be in any one of the 8 states. The agent might start in room A and both rooms are dirty. Maybe it starts from room B but room B is clean. Any combination is a valid starting point. So next we'll talk about the actions. It is a simple environment, right? So each state exactly has 3 actions. Any of the state, wherever state it is. Either it is in room A with dirt, with room B clean, any state. The 3 actions possible are it can move left, right or suck. Larger environments might include additional directions like move up, move down. But for this type of problem, 3 actions are more than sufficient. Okay, right. Next, now we will come to this transition model. It's one of the important concepts. The transition model describes what happens to the world when an agent takes an action. In other words, given a current state and an action, what is the resulting state? So, for a vacuum world, the transition model is straightforward but has 3 important edge cases. Suppose the agent is in room A. Moving left in room A, the agent cannot move anywhere. Okay. So the agent stays in room A itself. No state change. Okay. No state change. If it is moving left in the leftmost square. Suppose if it is moving right in the rightmost square. It's moving right in the rightmost square. Same thing. There is no place to go. So the agent is in room B itself. So this is with respect to room B. Okay. So again, no state change. Now, sucking in a clean room. Again, the room is already clean. It has no effect. The state space does not change. So these are the three edge cases, okay, that has to be considered. Okay. Now we talk about the goal state. The goal state or the goal test is very simple. We keep asking questions. Are all rooms clean? Yes, the agent has succeeded. If one of the room is still dirty, the agent keeps going and cleaning it. So what is the path cost? Path cost is defined as the number of steps taken. So for each individual action costs 1. If the agent cleans both rooms in 3 actions, the path cost is 3. But the ultimate goal is to minimize this cost. To find the solution with fewer steps. Okay. Now, it's a very it's a small, simple reflex agent program. So, what is returned here? It's a simple function. Here, the function takes 2 inputs. Okay, the agent's current location, whether either it is in room A or it is in room B, whether it's going to take A or B. Okay, and the current status, whether it is clean or dirty. So these are the 2 inputs. So what is the rule 1? If the status is equal to dirty, then you have to suck the dirt. Clean the current room immediately. Either you're going to be in A, clean it. If you're going to be in B, clean it. This takes the priority over everything else. Supposing if the status is not dirty, means it's clean, and the agent is in room A, then you have to take right. That is, go and check room B. Again, if this is also clean, then come to B, room B. You have to move left. Again, you go and check A. If this fails, then comes here and then you go check here. So that is the entire agent. These three rules plays the important role in cleaning the rooms. So you're not going to have any memory, planning or complex reasoning. Simple condition action pairs are implemented here. So this is called as the simple reflex agent. What it does, it maps directly from the percepts to actions using these condition action rules. What you perceive right now determines what you do right now. If there is a dirt sucked, if it is clean, move to the next room. Nothing is important. So this particular simple reflex agent works for this environment. It will eventually clean both rooms and then oscillate between them, checking for the dirt. So the environment considered here is static. So the agent's work is going to be optimal. Supposingly, imagine there are 3 rooms. Or Imagine if the rooms could get dirty again after it has been cleaned. So these are the actual exact questions that motivate more sophisticated agent architectures. So this particular agent is fine for a static environment with two rooms. What happens when it increases? Three rooms. Or there, what happens if the room gets dirty again and again? Okay. Now, here you can see that a simple, uh, what to say, it's a simple vacuum cleaner toy problem we have discussed already. So, here is a difference that has been shown between the single state and the multi-state. So, if you start in 5, this is your initial state. Then you go to right and suck it. This is only for this particular state. If you have multiple start states, like you can start at 1, 2, 3, 4, 5, 6, 7, any of the possible states, then your solution will be move right, then go to these and perform the actions. Okay. If you're here, your dirt is here. So move to the next room, clear the dirt. Then again you can stay in the same room or go back. So these are the possible actions for this multiple states. So the references are from Stuart Russell, Parag Kulkarni and Elaine Rich. So what we have discussed here is, we have discussed about the vacuum cleaner world. It's a small thought problem that talked about state, initial state, goal test, actions and transition model. Thank you.